Don't pay much attention to me, but if you can see the slides, that would be helpful. This talk is called Consciousness Down the Rabbit Hole, Entanglement, Space-Time Wormholes in the Brain. And the real subtitle of this is just how deep into physics do the roots of our consciousness go? And what's happening today, a growing number of scientists are comfortable with the idea that quantum mechanics plays a key role in brain processes, especially those associated with consciousness. And there are a number of specific proposals as to how quantum mechanics may play a role in the brain deep within the neuron, where there are structures, perhaps microtubules, which are of a size and structure that quantum mechanics may be important. But there are others that argue that the roots of consciousness go deeper still, beyond quantum mechanics, to quantum gravity, string theory, and unified field theory. And this has really been true since the origin of quantum mechanics, and some of the founders of quantum mechanics maintained that consciousness is fundamental, consciousness is primary. And Penrose specifically is an example of somebody who's been working on consciousness, the roots of it deep in the realm of quantum gravity. This is a striking conjecture for many reasons, but one that can be, to a good degree, explicitly shown using a remarkable principle called holographic duality. And you've probably all heard about the holographic universe. It's a term used sometimes a bit poetically, but it has a precise meaning, and we'll be talking about that a little bit later. The basic story is, as you know, the universe is structured in layers of creation, from the superficial to the profound, from the macroscopic to the microscopic, and the evolution of science over the last century has been to explore deeper levels of reality at the level of quantum mechanics, the world of atoms and molecules, the world of quantum field theory, which is somewhat similar in its structure, but really has quite different things to say, for example, about the nature of the wave function. This is the physics, the mathematics, the language, the logic that is required to understand the elementary particles. And then most of the focus in recent decades has been on the unified field, exploring the unified source of the diversified universe. When it comes to consciousness and when it comes to mind, in parallel with nature, there are different levels of human comprehension. And the mathematicians have been very good at identifying different mathematical systems, different mathematical frameworks that describe different, increasingly expanded levels of mind, increasingly expanded and profound levels of human comprehension. You're probably quite familiar with a number of these mathematical languages, mathematical systems, from the counting numbers to the whole numbers, which includes 0, to the integers, the negative numbers, to the fractions, the rationals, to the real numbers, to the complex numbers, to what are called function spaces, limits of function spaces, products of function spaces. Each of these describe infinities, like the counting numbers go on to infinity, but we're describing infinities of increasingly staggering size. And at the basis of the whole thing is the universe of sets, which you can try to define mathematically to some extent, but the mathematicians call this basically consciousness beyond comprehension. Bigger than any infinity. And what's been remarkable throughout the history of physics and mathematics is the degree to which this mathematics, these inventions of the mind, in deeper, more expansive levels of mind, correspond so perfectly to the structure of physics. They describe so perfectly the functioning of the laws of nature at deeper and deeper levels of quantum mechanics, quantum field theory. The proposal here, throughout time, I should say, is that human awareness at its core is universal. Individual consciousness, maximally expanded, is universal consciousness. But that's such a fundamental proposition that it's worth examining, could this be true? And there have been many arguments put forward, and I've certainly put forward some here in previous conferences, for that identity of, say, pure consciousness and the unified field, or Atman and Brahman. One is a very profound quantitative structural correspondence between what we call pure consciousness and what we call the unified field of string theory and M theory. And that correspondence is really quite striking. And I won't try to go through this today. We don't have time. I've been through it before. But the correspondence extends to both the structure of the material universe that emerges from the unified field, which is in terms of 3 superfields, which in turn comprise 5 fundamental spin types. There's a profound relationship between these 3 and these 5 to what are called the Pancha Mahabhutas, or the fundamental elements of space, fire, etc., and their natural grouping. It goes on. And the analysis also goes not just in terms of what comes out of the unified field, but the fundamental structure within the unified field. And that takes a little bit of going through. But basically what you find is this profound correspondence structurally, functionally, and quantitatively between the unified field and the fundamental reverberant frequencies within the unified field, or superstring field, and the fundamental reverberant frequencies of consciousness, both of which go through an elaborate internal dynamics as they prepare to give rise to the material universe on the one hand, or thought on the other. And that incredible structure, by the way, is mirrored in our brain, in the central nervous system, which has interesting implications we could talk about some other yuga. So basically, we have a profound quantitative and structural correspondence between pure consciousness and universal consciousness. And we also have what are called field effects of consciousness. Long-range influences of consciousness, which are seen, for example, in large meditating groups upon crime and social violence, has been studied and published many, many times. And additional psi phenomena that we're going to hear about shortly this morning, which are also strongly supported by careful empirical research. So field effects of consciousness are also supportive of this identity of individual and universal consciousness, but the question remains, how? How? And this has been the stumbling block of material scientists, physical scientists, for a long time. The question is, again, how can this human brain, which we associate with consciousness, access the unified field? To what extent is the brain quantum mechanical? That's something that's beginning to be understood. But to what extent is the brain so deeply quantum mechanical? That's the question we have to answer. Can this human consciousness access the unified field? So hold that thought. We are going to now, in the process of answering it, discuss a little bit some intriguing aspects of quantum entanglement, which is a fundamental theme of our conference this year. So a very brief discussion. What is quantum entanglement? Well, I'll give you an example. If you take a radioactive particle, an unstable particle, a spinless particle, and allow it to decay, it'll decay, for example, into 2 final state particles. Those final particles might have spin. And because the initial spin is 0, it was a spinless particle, the final spins have to be anti-correlated in order that their spins sum to 0 so that spin is conserved to be 0. Actually, what you get, though, when a particle decays is not just this or this. You get this and a quantum coexistence, a quantum superposition. And those 2 particles we're talking about could be halfway across the universe by now. And this all gets rather more curious when you introduce the effect of an observer on the system. So here is Alice, and Alice poses the question, right here in our laboratory, is the particle here spin up or spin down? And the act of performing that measurement, no matter how you do it, is to yield a classical definite result. So we'll either find that the spin is down or we will find that the spin is up. And that's a rather mysterious process I'm not going to talk much about today, but that's called the collapse of the wave function. But by conservation of spin, if this wave function collapses down, the other one must be up, and vice versa. And that's called entanglement. And you're having some kind of a long-distance effect simply by performing that observation here in the Crab Nebula, where the other particle happens to be. Einstein was a bit freaked out by that and ultimately rejected quantum mechanics due to this problem of what he called the spooky action at a distance nature of quantum mechanics. Can string theory shed a little bit of light on this? And it can, in a most intriguing way. Some smart people, Maldacena and Susskind, propose that quantum entanglement of separated particles is a consequence of space-time wormholes. What? Really? Now, this has actually been demonstrated for the case of charged black holes that are pair-produced in a strong electric field or magnetic field. So if you have a strong magnetic field that you can create in empty space, you can pop a pair of black holes out of the vacuum. You've pair-produced black holes. And those black holes that you've pair-produced are entangled with each other. And that entanglement is actually explained by the fact that these two black holes are connected by a wormhole. So here's black hole physics 101. A black hole is a hole ripped out of space, caused, for example, by the collapse of a massive star. And at the center of that hole, you have an entire star squeezed effectively to a point, and the strength of gravity is so intense that nothing can basically escape from it, nothing can communicate from it. It is basically removed from this universe. And that singularity is surrounded by a shroud called an event horizon from which even light cannot escape. This is the point of no return. Don't even dip your toe beyond the event horizon. And a wormhole is just a double-throated black hole connecting, opening up, where a black hole opens up into two different regions of the universe, here and there. Now, most wormholes, and it's these wormholes, by the way, that are supposed to be connecting entangled particles, or at least entangled wormholes for the moment. Most wormholes are non-traversable. That means, like a cockroach hotel, you can go in, but you can't go out. And the reason for that is, strangely enough, that the wormhole itself stretches and narrows so fast that you can't quite traverse it. Particularly because in the process, you've got to sort of snake your way past the black hole singularity, which is extremely difficult to do. And that's why the scriptures say it's easier for a camel to pass through the eye of a needle than for a particle to pass through a wormhole. Let's take a very quick look at this. Here is Alice, and there is Bob, long-lost lovers, separated by vast distances of space that happen to be connected by a wormhole. It's tempting to want to dive in. But you can show that you can't get through it without traveling at a speed, velocity v, faster than the speed of light. You can't get through it. And that's why the wormhole is said to be non-traversable. But it is interesting enough to if you study this, you realize that if Alice and Bob, deeply in love, are bold enough, both, to jump into the black hole and to do it soon, they can meet in the black hole, in the wormhole, connecting the two event horizons, consummate their romantic desires before they plunge irreversibly to their doom in the black hole singularity. But it is also worth briefly noting that if they are timid, if they are a bit timid, if I lost my sound? If they are timid and they hesitate, then all is lost. Because if they jump in too late, they will hit the singularity before they have a chance to fulfill their romantic fantasies. So, in summary, and this is really a summary, these space-time wormholes can explain the mysterious phenomenon of entanglement, at least between certain entangled black holes. But what these guys have proposed is not only that, but any entangled particle, any entangled pair of particles are connected by a wormhole. Wow. And these wormholes provide an explanation, to a degree, for the spooky action at a distance between these unconnected entangled particles by providing, you could say, a physical link between them. And this has now been explicitly shown using the concept of holographic duality, which is going to be very important, and I'm going to use it to illuminate this issue. Holographic duality relates physics, relates physics in our 3+1 dimensional universe, physics in our universe, to what's going on the boundary of our universe. So let's think we live in a giant tin can where the vertical direction is time and the horizontal directions are representative of the dimensions of space. And space-time has a surface or a boundary which is only two-dimensional plus time with a very different appearance. Does our space-time really have a boundary? It may not. We can always give it a boundary by injecting it with a small amount of negative vacuum energy. And this is something that we can do in principle, and it allows us to carry out the math we need to carry out. So yes, space-time does have a boundary, or can be given a boundary, and what holographic duality does is it relates physics in our three-dimensional world, we think we live in a three-dimensional world, to physics on the boundary of that world. So here we are. We think of ourselves as three-dimensional creatures, living in this 3+1 dimensional space governed by M theory. But if you take the particles in Stuart Hamerov's head and you project them out onto the boundary of space by putting a strong projector lamp behind him, what you will see is a swarm of activity on the surface, basically a swarm of particles living on a two-dimensional sheet. And that swarming of particles on the two-dimensional sheet is governed by a very precise physics, a very specific physics called ABGM superconformal field theory. It's an extremely simple and well-behaved quantum field theory in comparison to the immensely complicated M theory, which includes gravity, that governs our universe. Can we use this relationship? These are two apparently different but mathematically identical views of you and me. Are we three-dimensional creatures? Are we two-dimensional creatures? If one is true, the other is true. This is what is meant by string duality. Now, can we understand quantum entanglement a little better? We're going to relate physics in our world, which we're going to put on the boundary, to the physics in a 4+1 = 5-dimensional universe. We're just going to use holographic duality the other way around. And here in our universe, which is on the surface of this higher dimensional universe, are two entangled particles that we produce in a strong electric field, flying away from each other. And life in our universe is a little more complicated than that, because in addition to the particles, we also have what's called a quark-gluon plasma that shrouds the particles. A very complicated system. But now let's look at it from the interior point of view. Look at it from the perspective of the higher dimensional unified field theory or string theory, in which case these particles don't even exist and the quark-gluon plasma doesn't exist. Instead, it's all replaced by an extremely simple string. A string that is expanding and expanding, a string whose endpoints are glued to the surface of the boundary, and a string that is expanding, which helps us explain why these particles seem to be moving apart from the surface perspective. In this perspective, the entanglement, quantum entanglement that connects these two particles, that entanglement is actually carried by the string. You have to be careful in all of this, keep Einstein happy, and you have to keep Einstein happy, that it's not possible for these two particles to actually pick up the phone and talk to each other through the string. physically send to physically communicate through the string if that's faster than the speed of light. And if you go through this thing very, very carefully, you will see that that's exactly the case, that the information that you can send along the string is limited by the speed of light. In fact, take a look. Here are the two particles, but from the real internal perspectives, these are just the endpoints of a string that is expanding as time proceeds. If you try to send a signal from inside the string out to the particle at the end of the string, you'll never make it because the string is expanding too fast. You have basically the appearance of an event horizon on your string. At the same time, if you send a signal from the end of the string or the particle to the interior, and you quickly do the same from the other particle, they can meet in the center. But if you do it too late, they will never meet in the center. Does that start to sound familiar a bit? That's the structure of a wormhole. So the scientific way of stating this is these strings have the topology of a wormhole. They're great for correlations and entanglements, but you can't cheat Einstein. That'll keep Einstein happy. So the upshot of this is the long-range entanglement of separated particles, quantum entanglement, in 3+1 dimensions, where we assume we live most of the time, is a consequence of strings and wormholes in 4+1 dimensions. Strings connecting correlated particles help explain their entanglement without allowing causal communication, which is essential for Einstein causality. So to some extent, you can say that this entanglement in which there's nothing but mathematics that connects the particles, replacing that with an actual physical connection, despookifies entanglement a little bit, hopefully making Einstein, at this point, a little more comfortable with quantum mechanics. Now, what are the implications for our brain? Early this morning, Zaya was kind enough to offer her brain for the purpose of this investigation. And here is Zaya's very pristine brain living in our 3+1 dimensional space, which is where we believe our brains like to live. But this is just really the boundary of a higher dimensional space. And by the way, we're already assuming in my talk that the brain is quantum mechanical, meaning there are quantum effects or quantum correlations relating distant parts of the brain, even if that's inside a single neuron. But if that is true, then from the perspective of holographic duality, from the perspective of this higher dimensional internal space, those quantum entanglements, all quantum effects, in fact, in the brain, are described by strings and wormholes that develop on those strings. So in other words, for example, entangled microtubules within our neurons or any quantum effects involving entanglement within the brain can be explained in terms of, and are identical to, strings in higher dimensional 4+1 dimensional space-time. Which leads us to this conclusion. Quantum effects, like quantum entanglement in the brain, are identical to or dual to quantum gravity and string theory. If one is true, if quantum mechanics are there, the other is true. If quantum mechanics is relevant to the brain, then string theory and unified field theory are equally relevant. That is, if the roots of human consciousness extend to the quantum mechanical level, then they extend all the way to the unified field. That would mean that consciousness is fundamentally a phenomenon of the unified field. Or getting back to where we started, that Atman is Brahman, which means consciousness, human consciousness, at its core is universal consciousness. And that would, in turn, help us explain field effects of consciousness. Pay close attention to the next talk this morning. It would even allow us to explain things like the cities, supernormal abilities. For example, levitation. You can take any example, but this works. Levitation is a phenomenon of gravity. Or you could say it's a phenomenon of anti-gravity or defying gravity. But gravity is caused by what? The curvature of space-time geometry, according to Einstein. And where does that curvature of space-time geometry come from? It ultimately bubbles up from the unified field, the field of quantum gravity. And gravity at its foundation is quantum mechanical. Space-time at its foundation, gravity, space-time curvature at its foundation, is quantum gravity, which means it doesn't have a definite shape. It has a quantum coexistence of all possible shapes at once, which I've tried to draw this way. But how do you get from this quantum coexistence of all possible shapes at the origin of space-time to the flat and well-behaved structure of classical space-time that we see, that we think we live in? It's a process of statistical averaging. All these fluctuations are fluctuating at very high speeds. And if you have unless you have an extremely high-speed camera, all of this rapid oscillation and fluctuation is going to iron itself out. It's going to wash itself out into a blur. And that's basically that averaging process takes this space-time foam into classical space-time geometry. But if it were possible to actually function, if consciousness could access that level of nature, if consciousness fundamentally is universal, if consciousness has its roots in the unified field, if you could hold an intention at that fundamental level, you can upset. Instead of pure random fluctuation, if you could hold an intention, I'm thinking of the Zeno effect, at this level of nature's functioning, then you could tilt the averaging. You could upset the averaging out of all of these things, and you could start to develop something that emerges that is very different from what would have emerged purely probabilistically. So that space-time, instead of curving down in the vicinity of the Earth, may curve up, in which case you would fall up, not down, or forward, or whatever direction you choose. The conclusion of my talk is, just how deep do the roots of consciousness go, of human consciousness go? I would say they go all the way to universal consciousness, all the way to the unified field. Thank you. Thank you. Thank you. Thanks a lot. Thank you kindly. Thank you. So thank you very much. I think, believe it or not, we have a couple of minutes.
Probably the first speaker in the history of SAN in 6 years.
It's certainly the first in my history.
So we can ask a couple of questions. You want to direct me to where should I bring the mic for a couple of questions?
Yes, sure. There's a lady in the front row. There's a gentleman next to her.
Good morning.
Morning.
Thank you. That was wonderful. So when we're explaining entanglement, we're talking about two particles.
Entanglement, yes, go ahead.
Technically
yes.
party of two.
Right.
What happens with party of three?
Oh, they similarly could have entanglements. Often in quantum mechanical systems, they do have entanglements. Quantum mechanical systems can be very, very rich. We've only taken the simplest possible possibility. But Susskind et al. Go on to show that what you can have in a situation of three entangled particles or four is basically a network, a web, a network of wormholes, or a network of strings connecting all of those particles. They do some really remarkable calculations whereby, well, maybe I shouldn't go into all of that, but yes, these wormholes, and these wormholes can merge to form a bigger wormhole if somehow two of those particles happen to merge somehow. So yes, this wormhole connection works for larger numbers of particles.
Right, but the question, and perhaps this is not the right forum, and we can do it on the side, but how do they behave in party of three? Because you use the analogy of a couple that falls in love with one another. When you have party of three, they're going to behave differently.
Oh yes, but you know what? You can have a party of three. It's called a ménage à trois. This is the technical term.
I just stepped right into that one. I know, but I'm talking
and you
particles
can
now.
if you're connected by a web of wormholes, which is another way of saying if you're all entangled, you can, in the wormhole case, all meet in the wormhole, play out your menage a trois, and then plunge into the singularity. So, and this is what Susskind and Baldacena do in a very long article. It works.
Okay. Well, thank you.
Sure.
We have time for one more. Is
I
it
do.
okay?
I do. Sure.
Good morning.
Morning.
Is the concept of holographic duality extensible to higher dimensions in the string theory, all the way up to the 10th dimension? And if so, then can we take the brain in its current 3D and connect parts of it through higher dimensions? And also, can there be particles in all the higher dimensions which can be connected together?
All right, that's a compounding of questions. First thing is, holographic duality will relate physics in n dimensions to physics in n+1 dimensions. So we have just related physics in 3+1 dimensions to type 2 string theory in 4+1 dimensions. Could you take that same thing that's going on in 4+1 dimensions and recast it in a 5+1 equals 6-dimensional formalism? And the answer is, I think, yes. But remember that type 2b string theory in 4 dimensions will have to relate to a very specific theory, not just any theory, in 5+1 dimensions. And I haven't done that calculation. But because those dualities exist, then you could do the calculation and you would get a slightly different picture. In terms of how many dimensions you can do that, I don't know the state of the art into how many leaps of dimension you can do. There's probably some theory in each of those dimensions that might have a correlation. Whether those theories are sensible or not, I'm not sure. In terms of string theory, admits, typically speaking, likes to be formulated in 11 space-time dimensions. That's a little arbitrary, actually. I mean, in some respects, yes. But you really have freedom, really due to holographic duality, to formulate that theory in a different number of dimensions. And it'll look different. It may not even look like string theory. It might look like quantum field theory. So there is tremendous flexibility. What comes out of this is so much of what we take as reality is a viewpoint. And there are completely different points of view. Why do we experience ourselves as three-dimensional human beings when it may be simpler, more efficient, and equivalent to consider ourselves as two-dimensional creatures living on the boundary of some space? And people who've thought about this tend to say, well, it really has to do with our education. It has to do with how we're taught. We're given some basic ideas of how to think and how to view the universe our mother communicates and so on, and we develop a shared conceptual language. And that, quickly we wire our brains to see things in a particular way. And that's infectious. That is something that we socially all basically participate in. It could have been that instead our mother taught us about our two-dimensional structure and we would see everything that way. If you were a physicist, that would be fantastic because you wouldn't have to worry about gravity at all or quantizing it, which has been a nightmare. So I wish my mother had taught me about my two-dimensional nature. I never even learned a thing about my three-dimensional nature. Someday somebody might tell me, hey, you're also a three-dimensional creature. I'd say, get out. Forget it. Would there be any downside to that different point of view? I don't know, there may be. I don't know, maybe we've chosen the right way of thinking about ourselves. But it's just a point of view, and there are, in fact, many. Thank you.
John, do you want to take another question or two? Should we do that? Thank you. You can use this mic, and do you have another? 1 sec. You asked yesterday. Mark? Okay, 1 second. Can somebody bring me a second mic? Mark, can you shout on this? Yeah. The microphone too.
Sure. Hi, John. That was brilliant, as always. Just wanted to know what your thought was. There's some people like Samantha Lawton, Mangia, who say about there's black holes at the center of every cell, and people like Nassim Haramein and stuff. What's your view on there being black holes everywhere, as opposed to just out in space in the center of galaxies and stuff?
From the perspective of what we presented today, holographic duality, if we're willing to answer that question from a higher dimensional perspective, wherever you have quantum mechanics, you do have well, whatever you have entanglement and correlation are really the hallmark of what distinguishes quantum mechanics. Wherever you have that, you have strings and wormholes. And those wormholes do topographically and they do topologically have the structure of a black hole. So in some abstract sense, I think I can see it. I'd be careful how I use it and what conclusions I draw from it. So I'd have to look at it very carefully, line by line. But I can see that there could be, some substance to that. Yes.
It seems like the gentleman was asking since before. It was okay. Sorry, I want to be fair to you asked before. Yeah.
For your quantum mechanical functioning of the mind that you were discussing, like the correlations in the different part of the brain, how does that work in relation to time for like decoherence times at 37 degrees centigrade?
That is one of the key questions that continually confronts that field of quantum neurology. It's a very, very good question. And there's a lot of discussion and debate about it, back and forth in the literature. How long can these entanglements, how long can this quantum coherence or quantum correlation survive when it is so thickly embedded into the sloppy, warm, wet environment of the brain? And it depends a little bit. It's a quantitative question, and it's not an easy calculation to do. But having looked at it, a few times, and certainly looked at the arguments of people who are saying their calculation is sound, and somebody else saying, well, no, our calculation is more sound. My belief at this point is that you can have correlations, quantum effects in the brain long enough to be relevant to neuronal firing. Whether you can have correlations that are sort of across neurons, that I do not see. And sometimes that's talked about, but I don't think it has been demonstrated. But within a neuron could be good enough, because neurons classically affect other neurons, and you can build up a small effect that way, potentially into a big one. So these questions are really very much ongoing. It's a very interesting area, important area of research. Thanks.
So it's close by, it's easier.
I just wanted to follow up on her question about multiple entanglements among different particles. I know that in the black hole paradox discussion with Stephen Hawking and others, they talk about that you can't have three particles being entangled. And this results in that black hole paradox, the firewall paradox. Are you familiar with those arguments? So I'm trying to understand why three particles can't be entangled when clearly I thought they could be. And I was wondering if you could clarify that.
We'll see if sometime in the conference Henry Stapp would like to shed some light on that. But you have systems that are entangled that can be, the universe from the standpoint of quantum cosmology is all one wave function. And everything within that universe is inseparably entangled to the point where you can't view any part of the universe in isolation from another. Now, decoherence does happen as an approximation within that, so that you can start to distinguish one part of the universe from another in a relatively, approximately self-consistent way. But that's a counterexample to the statement that you can't have three entangled particles. I think that a quantum system, even a Bose condensation, a soup of superconducting particles, electrons, or superfluidity, you have many, many particles that are entangled, that many, many bosons occupying the same quantum state. So I think I'd have to look more carefully at the wording of the statement to see whether or not I agree with it.
Particles that appear to live outside a black hole, one of the pair falls into the black hole, the other goes off to infinity.
Yeah, I'm familiar with those arguments. I've been through the arguments, but I don't see that one. I don't see the way of putting it.
One more? Henry, you don't want to comment?
If one accepts the Penrose-Hameroff collapse mechanism by gravity, then when these entangled particles get far enough apart, won't the collapse take place by this gravity mechanism much sooner than what you've been talking about?
That is a very, very good question. In addition to, quantum gravity, according to Penrose's what? Hypothesis. Causes a collapse of the wave function. I do not believe that is true. But let's assume it is true. Then there will be a certain amount of time that particles of a certain mass especially will begin to decohere. And that may happen before other environmental influences take over. So there are two mechanisms for decoherence, you could say. You have the fundamental decoherence that might be caused by quantum gravity, but I don't believe is. And you have the environmental effect as well, which can cause not exactly a collapse, but a decoherence. And that's a little bit different. Penrose is trying to achieve a bona fide collapse of the wave function, where one alternative survives and the other disappears. Decoherence, basically, you still have the two alternatives existing, but they're no longer related or correlated or entangled with each other, and they sort of behave as if independently. Thank you for your questions. I better move on. Is Dean ready?
They told me he's ready. So let's do one quickly? No. Yeah. One more quickly? Yes.
As I understand it, decoherence, say environmental decoherence, is further entanglement of the superposed state with the complex system of the aggregate detector and so forth. So it's just the universe is full of transformations of entanglement. You never lose the entanglement in a sense, it seems to me. Maybe correlations get erased and replaced with something else. Does anybody have a story on this? Anybody can see that?
You can derive what is happening in those circumstances, and it's true that the system fundamentally should be governed by the Schrödinger equation, you could say, and will remain entangled and, in fact, increasingly tangled with the environment as it interacts more and more with the environment. And so what's happening with decoherence is that if we're willing to accept a certain amount of ignorance about what's happening to all those entangled particles which may now be halfway across the universe, and sort of sum over them or average over them and accept a little bit of ignorance about that which we cannot know, that which we will never measure, then what happens is you see decoherence taking place. But it is an approximation that involves accepting a certain amount of ignorance. It happens to be a very good approximation, and it happens to work well to explain a lot of what we see. Right. Correct. This is I can't hear you. I'm going to paraphrase that. It's a marvelous question. Then I must surrender the stage. From the ultimate standpoint, if the unified field, universal, the wave function of the universe is nothing but consciousness, and it probably doesn't even evolve with time. In fact, if structured properly, due to the Wheeler-DeWitt equation, there is no time in that eternal perspective. But what you can see arising within that perspective, which is undifferentiated wholeness without specific content, is the emergence of points of view within that wholeness. And those different points of view are alternative, approximately independently existing, self-consistent perspectives within one whole. So, you know, we're all just different perspectives within one indivisible wholeness, and those perspectives can exist due to decoherence, which gives you a little bit of independence from me, enough to allow you to think that you are a self-consistent, sustaining perspective. So this is, you know, really big now, and I wasn't going to get into this, but I think it's a very important point of discussion. Thank you.